Hello and welcome as we move into our next major area of study into inorganic chemistry. To start off today's lesson, we're looking at this concept of periodicity and linking physical properties to it. For our lesson objective, we're going to explain the trends observed across the periodic table, including atomic radius, ionic radius, melting point, electrical conductivity, and burst ionization energies, where we have our learning outcomes as always from the Cambridge curriculum just below there. So the periodic table is quite a feat of human genius. The amount of information that this table holds and the different ways that you can read it, and you will learn to read it as you continue your chemistry education more and more, it's quite astounding that something seemingly so, plain, for lack of a better word, can actually hold such an incredible amount of data and information. We're all familiar with, at this point, we're all familiar with what the periodic table looks like, so I'm sure this is nothing new to you, but we're going to look at some different ways to interpret it. So it's developed by this fella called Dmitry Mendeleev, and it's no over-exaggeration to say that this fella was an absolute genius of a human being. The fact that he managed to order and create the modern periodic table as we know it without having all the elements available to him. They weren't all discovered at the time that he made it, so he actually left gaps and he predicted where elements would be that hadn't been discovered yet, and when they were discovered, it turned out that he had predicted them with an astounding level of accuracy. But he even discovered it before scientists knew what the structure of the atom was. So nothing short to say that this fella was a genius. Unfortunately, we don't have the time to go into him right now, but I very much recommend that you go and do a little bit of research, watch some videos, because he had quite a fascinating life. But at this point, we know the periodic table, we got 18 groups being the columns, and we have 7 periods, plus our lanthanides and actinides down the bottom. And we arrange these in order of increasing atomic number, where we've got hydrogen with 1 proton, helium with 2 protons, lithium with 3 protons, so on and so forth. As we read left to right, we observe repeating patterns in chemical and physical properties, and it's these repeating patterns that we see that is the foundation of periodicity. That's what periodicity means, the repeating patterns that are observed in both the physical and the chemical properties. So we're starting today by looking at the physical properties that we observe. Now we're highlighting period 3 as our specific example we're going in depth in, but these patterns are just that, they're patterns that are observed across the whole periodic table. So we're looking in depth at the period 3, and we can extrapolate that more generally for the other periods in the periodic table. So there's a number of concepts that we need to be familiar with. The first of which is the atomic radii, which is exactly what it sounds like, the radii of an atom. Used to compare the size of different atoms, generally comes from an element's single covalent radius, useful for comparison purposes. So you imagine if you have 2 elements covalently bonded to each other, you've got the nucleus on each of them, and then you've got your electrons around it. You've got your covalent bond, because this is the single covalent radius. Then it would be the distance from both of the nuclei divided by 2 to get the covalent radius of the covalent radii. Now there are other kinds of atomic radii, for example the metallic or the van der Waals radii. But we're just going to be comparing the covalent radiuses because that's useful for comparison purposes. Now, argon being a noble gas doesn't really form covalent molecules, so we kind of just ignore argon as a bit of an anomaly because we can't get the covalent radius, we can get the van der Waals radius, but that wouldn't be the fairest comparison to compare. So what affects atomic radii? If we imagine that we have a size of an atom, it's my circle with my atom, electrons around it, I've got a nucleus in the middle. What's going to affect that? Well, it's going to be how many electrons it has, as in how many quantum levels it has. The more quantum levels, the bigger the radius is going to be. I don't think I need to go in depth on that, that's pretty obvious. It's also going to be determined by the number of electrons in the outermost shell, and it's also going to be determined by the nuclear charge, so how many protons are in the nucleus. One other small effect that comes through the quantum shells is we also have shielding from the inner shell electrons. We've looked at all these before, so we've just got to be aware of them. But because we're looking across the same period, that means that everything in period 3 that we're going to be looking at is going to have the same number of quantum shells, and it's also going to therefore have the same amount of shielding from those inner shell electrons. So it means the main thing that we're looking at is how the nuclear charge is changed as we go from the left to the right of the periodic table, and therefore how this is going to affect our atomic radii, at least to begin with. So let's have a look. We have a atomic radii which has a value for atomic number 11, which is going to be our sodium. So we're looking at atomic number 11 through to 18, sodium through to argon. If you ever think now, what do you think, based on these factors, what is going to happen to the atomic radii? Well, one of the things that we know about protons and electrons is that they attract one another, electrostatic force of attraction between positive protons and negative electrons. So if we have the same number of quantum shells and the same shielding, what we're going to see is what happens as we increase the nuclear charge, because that's what the periodic table happens as we go from the left and right. We're increasing the periodic charge, increasing the nuclear charge rather, and we're also increasing the number of electrons. So if we're increasing both the amount of positive and the amount of negative, that's going to increase the attraction between those. Now, because the distance from or I shouldn't say the distance, rather the number of quantum levels between our nucleus and our outermost shell is staying the same for a given period, if we have a increasing amount of attraction between more positive and more negative, we're going to see the atomic radii shrink, because those outer shell electrons are going to be more attracted to the nucleus, and therefore that's going to shrink the radii. And that's in fact what we see. So as we increase the number of protons, we add another proton, we add another electron, we see that electrostatic attraction being even stronger. That's going to hold the outermost shell closer to the nucleus. And as we continue, we see this trend go throughout until we get to our chlorine. Again, we're ignoring argon because we can't get the covalent radius for argon, so we're just keeping it a nice fair comparison. So yeah, we're keeping the number of quantum shells and shielding the same because they're all in period 3, but as we increase the nuclear charge and number of electrons, we increase the electrostatic force of attraction between them, and that will decrease the radii across the period. Here's a little diagram. We've got our period 3 that we're looking at, but we also see this because this periodicity is about all the periods. We also see these trends throughout the whole periodic table. Generally, these general trends, I might clarify, across the whole periodic table. So we can see that same trend occurring in the group 2. What about our ionic radii? A bit similar, but quite different. Well, this is going to depend on if we're forming cations or if we're forming anions. If we're forming cations, we are losing our valence electrons, and therefore we're essentially losing that valence electron shell. If we're becoming an anion, then we're gaining electrons and we're fulfilling the valence shell that we already had. So we can look at this in two parts. We can look at this at the cations, and we can look at this through the anions, all through period 3. So our cations will be smaller than anions. Let's think about this. They have lost the electrons in the outer shell and therefore are down a quantum level. If we think about a substance that will form a cation, for example, our sodium, not the right amount of quantum levels, but let's just go with it anyway. If we have one valence electrons, and if we lose that valence electron, we're going to lose that entire quantum level, aren't we? Now, unlike the atomic radii, when we have the ionic radii, we are in fact changing the number of quantum shells. So our cations are going to be smaller for that very reason. We're going to have less of a quantum level because we've lost that outermost quantum level, and we will also have less shielding effects because we now have less electron shells. And the ionic radii will also depend upon the charge that the ion forms. So if we form a +1 ion, a +2 ion, or a +3 ion, for that electrostatic reasons that I talked about in the atomic radii section. So let's have a look at our first 4, where if we form cations, where if we form a sodium cation, then we form the magnesium cation, then we form the aluminium cation, and then if we were to form a silicon cation. So we're going to have More positive charge as we go from the 1 plus to the 2 plus to the 3 plus to the 4 plus. So that's going to see a decrease in the ionic radii as the magnitude of the charge becomes greater. It's going to hold the remaining electrons closer to it due to the fact that we're increasing the positive charge. So therefore, the higher the positive charge, the more tightly it's going to hold the remaining electrons that are still around it. Let's consider now our anions. Anions are the opposite of our cations in so much as they're gaining electrons as opposed to losing electrons. Now our anions are gaining electrons into the quantum level that they already have. So by this very definition, the anions of the same period to the cations are going to have a whole quantum shell extra, because unlike the cations that have lost the electrons and therefore lost that valence electron shell, our anions have kept the original number of quantum levels, but they've just gained electrons into that original valence shell that they had. Now, a few things to consider here is that we've still got the same original number of quantum levels, and we've still got the same nuclear charge that the atom would have. So the size of the anions is going to depend on where they will be, where there will be a large repulsion due to negative electrons, because we now got more electrons than the protons, and the nuclear charge will also have an effect. So let's have a look at this. As we enter the right-hand side of the periodic table to our nonmetals, our nonmetals form ions because it's closer for them to have a full valence by gaining electrons as opposed to losing electrons. So that's what we see here. We see our phosphorus, number 15. We see a big increase between 14 and 15 because we still have the original number of quantum levels, whereas our cations have lost a level of quantum, have lost a quantum level. So they're obviously going to be different sizes because of that. Now, let's think about this. We've also still got the same number of protons, 15 protons, but it's now got 3 extra electrons. Those electrons in that valence shell are going to be very crowded, and they're going to be repelling each other. So that's going to also increase the size of the atomic radius, the ionic radius rather, as well. Then as we increase the nuclear charge, we see the radii decrease. So there's going to be more nuclear charge, so that will shrink the ionic radii as that becomes greater. Notice we have no argon here. That's because the argon is a noble gas. It doesn't readily form an ion. Now, let's look at a few more physical properties. So we've looked at the atomic radii, we've looked at the ionic radii. Let's look at the melting point and the electrical conductivity. Melting point and conductivity also show periodicity. We can rationalize values based on the kind of bonding structure that they will exhibit. And this will also come into play a lot in our next lesson, looking at the chemical properties, the type of different bondings between our metals and our nonmetals and our metalloids is going to influence the periodicity that we observe. So let's have a look at here. We have our metals on the left-hand side. If I go back to my periodic table, actually, let's do this. We have our metals on the left-hand side. So sodium, magnesium, aluminium, metals, they're going to be the metallic bonding model. Our silicon tends to be a macromolecule where it will have a giant covalent structure. Then to the right-hand side, when we go into our nonmetals, we have our simple molecules. We have our simple covalent molecules, and then our noble gas that has just the monoatomic atom because it's already got the full valence shell. So as we go from the left to right, we see a decreasing metallic character, and that's going to have big implications for the melting point and the electrical conductivity, because we've looked at how these physical properties manifest due to the type of bonding model that they will have. So let's look here. I got a couple of graphs. I got a table over here. We're going to look at the melting point in Kelvin and our electrical conductivity in Siemens per meter, which is just, the higher the value is, the more electrical conductivity is. We don't really need to worry too much about that value, just the fact that it's going to be big or it's going to be small, depending on if it's a good conductor or if it is a bad conductor. So let's first look at our giant metallic substances. So our giant metallic, we're going to have our metallic bonding model. Our metallic bonding model, we have cations with a sea of delocalized electrons. So we form the cation. So for example, let's say this is sodium metal. These are all sodium cations, and we have our delocalized electrons that are free to move throughout it. We know that there's a strong force of attraction between our delocalized electrons and between our cations. This means it's a very strong lattice. This means they have very high or higher melting and boiling points than our nonmetals. And we also have charges. We have charged electrons that are free to move, so they are good conductors. We can rationalize the trend we observe based on the charges and the amount of delocalized electrons that we have. So it depends on how many delocalized electrons and the charge. So let's have a look here. For our giant metallic substances on our period 3, looking at the melting point, we see a general increase in the melting point. Now we can rationalize this due to the fact that we're increasing the number of delocalized electrons and also the charge on the cation in the metallic bonding model. If we have more electrons delocalized and we have a higher charge, that's more negative and more positive, that can electrostatically attract to each other, so that's going to make that a much stronger force of attraction. Consequently, that's going to mean more energy to break that apart. That's going to mean a higher melting point. So that's what we see here. We have our 1+ sodium in the metallic lattice, 2+ magnesium, 3+ aluminium. As we got more delocalized electrons, as we have a higher charge, we have more electrostatic attraction, requires more energy, therefore a higher melting point. Now we see the same thing in the electrical conductivity for the same reason. Electrical conductivity is just a flow of charged particles. The more delocalized electrons, the more we can conduct. So if we compare sodium, that each sodium atom contributes 1 delocalized electron compared to an aluminium where they're contributing 3 delocalized electrons, that's going to mean more delocalized electron, a higher electrical conductivity, and that is indeed what we observe. So they're our giant metallic ones. Then we get to silicon, which likes to make a giant covalent structure. Now it's also a metalloid and it's also a semiconductor. If we think about the melting point, a giant covalent structure will only have covalent bonds between all of the atoms within the structure. Covalent bonds are very, very strong. Giant covalent molecules have very high melting and boiling points for this reason, because it takes a lot of energy to disrupt that giant covalent structure. And that's what we see with silicon. We see a very high melting point because of this structure. Now, silicon is a metalloid, which means it has certain properties of the metals and the non-metals. It's that staircase that bridges the two parts of the periodic table. And it is in fact a semiconductor, so it can conduct. However, it's nowhere near as good as our metals. We don't have to go into too much detail why it can conduct, just need to know the fact that it is a semiconductor. Great, then we get into our simple molecular. Now, where I said that covalent bonds are really, really strong, intermolecular forces aren't very strong. So if we have a molecule, we have a simple molecule, such as, chlorine, Cl2, we've got one covalent bond between 2 chlorine atoms. The covalent bond is very strong, but if we have multiple chlorine molecules, these intermolecular forces between the molecules are weak. If we have weak forces between the molecules, that means we have a low melting point because we don't need very much energy to disrupt those forces. So we have our phosphorus, sulfur, chlorine, and argon exist as small molecules in the case of phosphorus, sulfur, or chlorine, or a monoatomic, which is in the case of argon, where we're going to have weak van der Waals forces. We've looked at intermolecular forces before. Van der Waals are very weak, doesn't take very much energy to interrupt them. Now these are going to be dependent on the number of electrons. So we see a little bit of discrepancy here, where we've got an increase from the phosphorus to the sulfur, and then decrease from the chlorine to the argon. And we can rationalize that based on how many atoms there are in the small molecules. Argon is just one atom. One atom means there's just one atom's worth of electrons. That means that there's only so many van der Waals it can make between the monoatomic atoms. Chlorine is a diatomic. We have 2 atoms. That means that we've got more electrons because we've got 2 atoms. 2 atoms is going to have more electrons than 1 atom. So we've got more electrons, so we're going to have more van der Waals forces between them. So the reason why we see this little discrepancy between the phosphorus and the sulfur, which sort of goes against this downward trend, is due to the fact that phosphorus exists with this 4 atom small molecule, whereas sulfur with this 8 atom small molecule. So the same reason, if argon's only 1 atom and chlorine's 2 atoms, we're going to have more van der Waals in the 2 atoms because there's more atoms. The S8 is going to be the highest of them because we have 8 atoms as opposed to the 4, the 2, or the 1. More atoms, more electrons, more van der Waals, more forces, therefore more energy to disrupt when we melt it. One thing that we know about our molecules is they are very, very poor conductors, or they can't conduct at all, and that's what we see. Very, very small amounts of electrical conductivity, or no amounts of electrical conductivity. Now we move on to the final physical property that we're going to relate to our period 3 elements, which is the first ionization energy. We have looked in depth at ionization energy earlier in the course, so this will serve as a bit of a recap more than anything new. We looked more in detail at the second period, so now we're going to look at the third period like we have been for the other physical properties. To recap, ionization energy, the energy needed to ionize the first time. That's all it is. We've looked at the period 2 first ionization energies earlier in this course. Now the period 3 elements show the same periodicity. Now again, that's why it's called periodicity, because these trends are observed across the periods in the periodic table. So what do we have? Like I said earlier, we've got the same number of shells, we've got the same effective shielding. The difference that we're having is an increase in nuclear charge across the period. So we can see this trend where generally we increase the ionization energy as we move from the left to the right. Now this is because of the increasing nuclear charge. If we have more nuclear charge with the same amount of shells and the same effective shielding, it's going to take more energy for a higher nuclear charge because the electron is more tightly held by that nucleus with more positive protons in it, because positive and negative attract each other, as we've been saying all throughout this course. But what we've got to be aware of is we see two dips that go against our trend. Now, how can we rationalize this? In fact, if you wanted to have a pause and maybe posit to yourself why we see these trends between magnesium and aluminium, and also between, that's phosphorus and sulfur. You can have a pause, and I'm going to tell you right now. It's because of the sublevels to begin with. So our sodium and our magnesium are in the 3s subshell. If I go back up to my periodic table, we have our S block on the left-hand side here. So sodium is going to have the electronic configuration of neon. If I write this up shorthand on the board, we're going to have the electron config of neon, and then we're going to have 3s1. So if I was writing sodium, we would have argon, and then we would have what am I doing there? We would have 3s1. If I was to then do magnesium, we would have argon and 3s2. When we move over to the aluminium, we have now entered the P block. So we would have, for aluminium, so this would be sodium, this would be magnesium. Aluminium now has the config of argon, 3s, why do I keep writing S there? Silly thing to do, 3s2, 2p1. So we've now moved up an energy level in our subshells, which if we think of it in terms of energy, if I do the 3s is going to be there. Our 3p's are going to be a slightly higher energy there. So if we go back to our trend here, if I skip forward, go past all these graphs that we've looked at, past the melting point conductivity, back to my ionization energies, we see a drop here because even though our aluminium has a higher nuclear charge than our magnesium, so we might expect it to have a higher ionization energy. In fact, we see the P subshell is a slightly higher energy than the S subshell, so that makes it a little bit easier to get rid of. So that's what we saw there. We saw the 3s increasing atomic charge from sodium to magnesium, same outermost subshell. But then we go to the P subshell, we see that decrease there because we're now in a P subshell, which is a higher energy, and we have the increasing atomic charge from aluminium to argon. But we have this other discrepancy between the phosphorus and the sulfur. So the same way that we have stable configurations for full shells, we also see stable configurations for half full shells. This is something we've seen earlier in the course as well. So if I were to write out the subshell config from 3s for our period 3, we'd have sodium, 3s1, magnesium, 3s2. Then we would have aluminium, where we enter the P subshell. Then we have silicon. Then we have phosphorus. Remember, we fill our empty orbitals before we pair up, spin pair up. So what we see here is for phosphorus, we have a half full P subshell, which is a stable conformation, which means that even though sulfur has a higher nuclear charge than the phosphorus, the half full P electron config subshell, this being half full, is more stable than the sulfur, which if we add one more here, we've now got a not a half full. That now becomes less energy even though it has the higher nuclear charge. So that's the little discrepancy we see here. And then as we fill the rest from sulfur, we get chlorine to argon. And then we have a nice full octet. And with that, we have finished our first lesson in inorganic chemistry and our lesson on periodicity of physical properties. What have we looked at? We have described qualitatively the variations in atomic radius, ionic radius, melting point, and electrical conductivity of the elements. Explained qualitatively the variation in atomic radius and ionic radius. We've interpreted the variation in melting point and electrical conductivity in the terms of simple molecular, giant molecular, or metallic bonding of the elements. And then we've explained the variation in the first ionization energy. Here are your tasks for this lesson. You can pause now, work through each of these starting from the bottom and working your way up through the columns to consolidate your understandings of periodicity. Thank you very much. I will see you in the next one as we continue our look into periodicity, looking instead at the chemical properties as opposed to the physical properties that we've looked at today. Have a great day.